Okay, so this video covers the fundamental theorem of calculus. As you can imagine, it's the fundamental theorem, so it is fundamental. It's very important. It's a foundation for a lot of things. So just a couple of notation things. Remember how this is little f and this is big F? Well, if I was looking at big F of x, and I was going to take the derivative of that, so derivative with x, respect to x, that would be little f of x. So for those reasons, if little f of x is integrated, what do you think it's going to come out as? Just basically, if you take the antiderivative of little f, you get capital big F of x, plus a constant. So what's happening is you're basically, if you look at this right here, you're taking the antiderivative of this, and you're plugging in the top number, and you're plugging in the bottom number, and you're subtracting them. So why that is, we'll get into a little bit later. We'll show kind of how that works, but for now, we're just going to kind of apply it, just use it. So you're anti-deriving, and you're plugging in these numbers and subtracting them. This you don't have in your notes, but it's a pretty good representation of like how to do the fundamental theorem. Again, it's fundamental, so it's very important that you understand it. You need to get your antiderivatives down, like the back of your hand, and kind of know that. So you can find a definite integral if you can find an antiderivative. So a definite integral means it has a number here, let's say for example 3, and here. This is a definite integral now, because of these numbers. That's what makes it definite. Now if I erase this, that becomes an indefinite integral of whatever we're taking the integral of. So today we're going to start doing definite integrals, which gives you the exact area, as you know, under the curve, and you're going to be able to do it with antiderivatives, and it's going to save you some time. So if you look here, what's happening is that you're going to take the antiderivative, and this is a little bit weird, but this is how the notation works. So this is step 1, this is your problem that you get, and this is step 2. You take the antiderivative right here, and you go from B to A, you make these bars. I'll do that in a second. And then you plug in and you subtract the two problems. So like for example here, they're doing the integral from 3 to 1 of x to the third dx. We know that x to the third is antiderivative of x to the fourth over 4. So what you're going to do is you're going to put a straight bar here, and you're going to put the number of 1 and 3. So this would be step 1. You'd solve it to this, step 2, right? And then you would basically just plug in 3. So 3 to the fourth over 4. And then you plug in 1. So 1 to the fourth over 4. So we're plugging in for x. We're plugging in the 3, and then we're plugging in the 1. And then we're just going to subtract those. So see what's written in red there at the bottom? All you got to do is do that arithmetic out, and you are done. Okay. You don't need to put your plus c when you do a definite integral, and I can show you in class if there's time why that is. But we might not get to that if there's not time. You can see it down there on number 3 of this printout thing. Okay, so let's do some problems. So let's start with A. So what it says basically is evaluate the definite integral. So let's talk about it. We need to antiderive this. So the antiderivative of that is x to the third over 3 minus, not plus, minus 3x. Okay, and that's done. So now here's the notation that you would need to understand. Squiggly bar becomes straight bar. This is just how they notate it. And we put the numbers on it, 2 and 1. So what that means is I want you to take 2, I want you to plug it in. I want you to take 1, I want you to plug that in, and I want you to subtract the results. So let's try it. So we're plugging in here. So let's think about it. We have something to the third over 3 minus 3x. And now we're going to subtract this whole thing, which is something to the third over 3 minus 3x, right? We don't want the x there or there. So let's replace our x's with these numbers. So here we replace with 2. So it's 2 to the third minus 3 times 2. And then here we replace with 1. So it's 1 to the third minus 3 times 1. I might have made that a little more overcomplicated than it even needs to be. You're just plugging in the top number, putting a minus sign, and subtracting everything from when you plug in the bottom number. A common thing that happens here is if this number is 0 down bottom, a lot of people forget to subtract out the bottom number because they think it just goes away because you plug in 0. And a lot of times it does, but not every time. So just be aware if the bottom number is 0, it doesn't necessarily mean you are free from doing the second part of this problem. So now we're just going to do arithmetic, so you got to be pretty good with that. 2 to the third is 8, so it's 8 over 3 minus 6 minus whatever this comes out to. So that's 1 over 3 minus 3. So it looks like our answer is going to be 8 over 3 minus the 1 over 3, if you think about it. So I'm going to do that right now. I'm going to do 8 over 3 minus the 1 over 3, so I have 7 over 3. I'm distributing that negative. And then I'm actually going to have a plus 3 here, so negative 6 plus 3 is negative 3. I guess that's 7 over 3 minus 9 over 3, so negative 2 over 3. So the calculator should get you that same answer. That's what we're trying to get to. So let's see how we're doing in time. We got a couple more minutes. We can try a couple more problems. So let's see if we can try this next one. I just want to show you quickly. I don't want to do this whole problem. But what would the antiderivative of that be? Well, this is equal to 3x to the 1/2. So it's going to be 3x to the 3/2 divided by 3/2 from the numbers 4 to 1. So then it's just plugging in. So I'm going to try to save you a little bit of that time. Now, by the way, you're always going to start, instead of dividing by 3/2, you're going to start just multiplying by 2/3, like in your mind, quickly, and it's going to save you some time. Now you have something simplified you can plug in and work from there. So let's look at this next one. From 0 to pi over 4 of secant squared. So it's from 0 to pi over 4 of secant squared of x dx. Okay. What did you derive to get secant squared? So you took the derivative of tangent of x. So that's your antiderivative, and you would want to plug in from 0 to pi over 4. So simple as they come, we just take pi over 4 and plug it in. So we have tangent of pi over 4 minus. I like to put a minus in the parenthesis like this, and then plug in the 0. And that's tangent of 0. Now, by the way, tangent of 0 is 0, so that goes away. This becomes just nothing. Tangent of 0 is equal to 0. But that's not always the case, so just watch out for that. So we just have tangent of pi over 4. And that is, I think, root 2 over 2, or 1 over root 2. And that's the answer for that integral. So what you're going to do is you're going to try a couple of these. Should be on your handout. So these are the problems. This integral here, pretty basic. Anti-derived, plug in those numbers. And then this integral here, okay? So maybe pause the video, give those a shot, and then we'll move on. You can see these answers in the back of the book to see if you understood what I did. And if not, you can flip back and watch again. I think we'll stop it here. We'll keep this video short, and then we will take care of it in the next one.